push that rock with some math, applications of determinants. Here we have a quadrilateral on a plane determined by the vertices, which are vectors in 2 dimensions. And determinants are in this formula for the area. Now, of course, we could find the area of a quadrilateral, but just picture a polygon maybe that is determined by 50 or 100 vertices. So it's a very complex polygon, and you want to know the area of it. Well, you could program a computer with this formula, and all you'd have to know is tag in the vertices, and it could spit it out. And a deep question is, why does this formula work in mathematics? But for right now, we're just going to be satisfied with computing it. Now, notice how the pattern works. It's the first vector, second vector, third vector. So it should be then on and on. So then it should be third with fourth. So what's happening is you're taking you have to go counterclockwise, by the way. So I got to go this way. Excuse me. So you pair the first with the second with the third with the fourth. And you keep doing that until you wrap or back around. So the fourth with the first means I stop. So I should have -1, 2, and I could have started anywhere, by the way. I just chose to start here. So I have -1, 2 mapped with 9, 1. Then I get 9, 1 paired with 4, 5. I said mapped with, I meant paired with. And then it should be 4, 5 paired with 1, 6, and then finally the last one, because I'm coming back to the beginning, is 1, 6 paired with -1, 2. Now I get those determinants. Well, that's -1. Remember, you go this times this, so that's a -1 minus this times this, that's 18. Plus 9 times 5 is 45 minus 4. Plus 4 times 6 is 24 minus 5. And then plus 1 times 2 is 2 minus a -6. And then all of this is inside a pair of parentheses being cut in half. So here I have -19, and here I have 41. Here I have 24 minus 5 is a 19, that's convenient. And then over here I have 2 plus 6 because of the double negative, so that's an 8. So 24 minus 5, oh, that's a positive 19, and here's a -19. How convenient is that? And this sum is going to get cut in half, remember. So we have 41 and 8, which is 49. So it's 49 halves, or 24.5 square units is the area. Well, that computation is rather boring. The exciting thing is seeing that, you can imagine surveyors being given a tool programmed with this little formula in it, and they can just ping a bunch of locations and they can get an area. Another cool application, maybe I should have the light on. Another cool application is finding the equation of polynomials. Well, I'm going to do the simplest case, and we won't have to do anything more difficult than this. But for a linear polynomial, you'll just need a 3 by 3. For a quadratic, well, this is going to get larger. We'd need x, y, and a y squared, so we'd need 3-dimensional vectors, only because we'd need an x, a y, and the y squared, and we'd have a column 1. So it gets more complicated for more complicated polynomials, but we're just going to get a first-degree polynomial, a little line, mx plus b. We're going to get the equation of this line, which we learned how to do more easily in 7th grade, but we're going to use this cool new formula. So to do that, I need to plug in my first vector. Well, actually, the vector is going horizontal this time. So I'm going to plug in 1, 3. So I have x, y, and 1. Then I have 1, 3, 3. And then this is column's always 1. And then the next one, the second vector, is 2, 1. So 2, 1, 1. So those are the points on the line. I pick 2 points on the line and I plug them in as my vectors. And now I need to find this determinant. Well, one method that we learned was to copy down the first column as a 4th column and the second column as a 5th column, and then find this diagonal product, the product of these diagonals here. So the 1 times 3 times x is 3x, 2 times 1 times y is 2y, and a string of ones multiplied together is 1, and then you add those up. Then you find these products, so that's going to be 6x, we're adding them together, and y. But we go this sum minus that sum up there, and remember this determinant is equal to 0, so this is the determinant's equal to 0. Now I'm going to simplify, so I have 3x plus 2y plus 1 minus 6 minus x minus y equals 0. Well, you combine your like terms and you have 2x, and you have a y, and then 1 minus 6 is negative 5. And if you wanted to look at slope-intercept form, well, you just subtract the 2x and add the 5, and there it is. There's a linear equation. Notice the slope is negative 2. Sure enough, we go down 2 and over 1. Math made simple. It's Simpson Man.